Hello everyone. In the last lecture we started a new topic, power spectral density, and today we are going to continue with some exercises on power spectral density. Today's session is going to be a problem session. Before we begin, I just have a few announcements. First of all, I corrected a few things in the lecture notes. So the version you will find below the video now is the updated version. So if you have already printed them, it doesn't matter. I'll just tell you as we go through the notes where to make the modifications. If you haven't printed them, just print this new version. Another thing is, as I said, today we're going to have a problem session. So let's say that it's up to you to decide on the speed or rhythm that you're going to use to follow the exercises. So what I propose is, what I will try to do is I will from now on, whenever we have an exercise session, I will just comment the time instant where each problem begins just below the video in the description part, so that if you have looked at the examples beforehand, you could just go to the time instant of the video where you can listen to the exercises that you have selected. I hope this is going to make it easier for you. Okay, so let's begin today. So what we are going to look at is the power spectral density applied to some problems. So we will first have a couple of continuous time examples and then discrete time. But before we begin, let's look at the following notes. So we have this basic relation here between the autocorrelation function of a random process. So in our setting now that we are considering, we have a wide sense stationary random process for the moment in continuous time, and we also assume that our process is ergodic. So actually the formula that you see here holds in general for any wide sense stationary process. How do you see that? Just look at the autocovariance function of the random process. We know how to write as the long expression and expectation of x of it's actually the covariance of x of t plus tau and x of t considered as two random variables. If you just decompose this expectation expression, you can just rearrange the terms and then obtain that cx is equal to rx minus eta x conjugate, so that you can rearrange the equation in this way. This is quite easy to do. We have seen this before. Now, the trick is that let's see what happens when we plug in tau equals 0 to this equation. So if you just put tau equals 0, you have Rx of 0 equal to Cx of 0 plus the mean value square of the process. Now, what we will do for ergodic random processes is from now on, well, we have already seen that if a process is ergodic, this part Rx of 0 is called the average power. This can be interpreted as the average power. Why? If the process is ergodic, the time averages are equal to the expectations, and Rx of 0, remember that it can be, well, let's maybe review that. Rx of 0 can be obtained by integrating the power spectral density of the process here from minus infinity to plus infinity, and then you have all this chain of equalities that hold when the process is ergodic, and this expression is called the average power. This is what we saw in the last lecture. Now, coming back to today's topic, where was I? Here. So we already know that this was called the average power. Now what we will do today is we will decompose this power expression into two terms. So into an AC term and a DC term. So this constant term in here, we will call it as the DC power. And the term that would normally change with tau, if we had tau as in the original expressions, the non-constant term is going to be called the AC power. Well, just a little motivation about or intuition about why we can interpret these terms as the AC power and the DC power. Let's just think about a random process. So let's take an arbitrary continuous time random process x of t. Well, x of t, we assume that this is a wide sense stationary process, so it has a constant mean, eta x. And where typically what does random process do? It has some variations around the mean value, right? It will do something like that. It will fluctuate around the mean value. Well, in each realization might look different, but typically a realization will look like this. Now, it turns out that you could actually, if you actually decompose this random process into two terms, the first term will be this constant value, the mean, and the second term will be the remaining, the oscillating, the fluctuating part. So you could actually write this process as the sum of, well, let me just not call these two things anything, not to complicate things. So we could write this process as the sum of two processes. The first process will just be the process of fluctuating around zero. So I'm having some behavior around zero. This AC part, let's call it, plus then there will be second component of this process corresponding to this DC value, the mean value, and we can call it eta x. So these two things, these two components, when you sum them up, it's going to give you the original process, and this second term has a constant value. It's like a DC function, a DC signal, and then this process is the original process minus the mean value. Now, I guess you would agree that such a decomposition, when we look at such a decomposition, it would make sense to call this DC part and then this the AC part, all of you are in a random setting now. Well, now, what you can show is the following. So, you have the average power of this process, right? P out, what is it? It's the Rx evaluated at tau equals 0. Now, you can show that the average power of this process would be the sum of the average power of this process plus the average power of the second component. Well, the average power of the second component will be nothing but eta x magnitude square, so this part, hence called the DC power. And then the average power of this second process is going to be called the AC power. But then you might ask, well, how do I know that this is equal to Cx of 0, Cx of the original process? Well, actually, the trick is the following. If you subtract the mean, let's compare these two processes. So the original process, x of t, has some autocorrelation function, Rx of tau. Then if you look at the autocorrelation function of this AC part of the process, the autocorrelation function of this process is going to be the same as the autocovariance function of the original process. So this is why when you look at the average power coming from this part, is going to be the same as the Rx of this process at 0, which is equal to Cx of the original process at 0. So, I mean, long story short, take any process, you can do this, take any White-Sun stationary ergodic process, you can do this decomposition. So the average power is the total power, is the AC power plus the DC power. So this decomposition always holds for White-Sun stationary ergodic processes. Now, going back to the notes, well, actually what we could do is, we could just go back to this equation and also interpret the same equation in the Fourier domain. So imagine that you take the Fourier transform of all of the sides. So taking the Fourier transform of the ACF, you get the power spectral density. And the second term would have some Fourier transform, so Fourier transform of Cx of tau, some function of f. And then you have this last constant term in here. So this constant term is going to appear as an impulse in the Fourier domain. And the strength of that impulse is going to be the constant value here, eta x squared. Now, well, this was one of the modifications I made in the text. So if you have already printed them, as you printed them last time, you could just maybe modify this sentence just to update it in the following way. So what this remark tells us is the following. So if you have an ergodic process, and if you look at the Fourier transform of this equation, which is obtained as in here, the trick will be that this first term here on the right-hand side will not contain any impulses at f equals 0. It could contain impulses for other frequencies, but at f equals 0, so at the DC part, it will not contain any impulses. All the impulses will be present in the second term, which comes directly from the DC part of the random process. Well, why is that? So actually, this is a property of the ergodic processes. If you have a White-Sun stationary and ergodic process, if you look at the autocovariance function of the random process, this function, just consider this as a function of tau. This function will not have any DC offset. Well, the DC offset of this function Cx of tau is going to be 0. Well, what does this mean? It means that, well, there are some possible typical cases. So Cx of tau could be oscillating around 0, around the mean value 0. Or Cx of tau could have some transient behavior with tau, and it could converge to 0 as tau approaches infinity. But what cannot happen is that this function Cx of tau cannot converge to some constant other than 0. So this is what we mean by saying that the autocovariance function cannot have a DC offset, cannot have a non-zero DC offset for ergodic processes. So this is kind of convenient, because imagine that somebody gives you the, well, you don't know the expression for your random process. Somehow somebody gives you the power spectral density of the process, or you estimate it by some means. What you can do is you can look at the power spectral density, and you would immediately know what is the AC power and the DC power of your process. How is that? You'll just look at, you'll look whether Sx of f contains an impulse at f equals 0. So if it does, the strand of that impulse, eta x squared, is going to be the DC power of your process. You're sure about that if your process is ergodic. And otherwise, the remaining parts, if you just integrate the remaining parts, you're going to get the AC power of the process. This is actually practical. We will see some exercises on that. Now, okay, so let's look at a couple of examples now. So, in this first example, we have this random process, a cosine, some cosine function with a certain given deterministic frequency plus some phase. What is random in this process is only the phase term. The phase is uniformly distributed between 0 and 2 pi. Actually, we have solved this example before. We showed that this process is White-Sun stationary, and also we showed that this process is ergodic. And we found the mean function of the process is equal to 0, and we found the autocorrelation function of the process. Now, what we are asked to do here is to decide to determine the power spectral density, and look at some properties of the power spectral density. So it's going to be a review of some properties we saw last time. Okay, so let's solve this question. So, well, actually, this is a quite an easy exercise. So, well, we know that the power spectral density is we should just take the Fourier transform of the autocorrelation function Rx of tau. So, Rx of tau is a squared over 2 some cosine function. So, a squared over 2 it could go outside the Fourier transform. Fourier transform is linear. So then I will be taking the Fourier transform of the cosine term. 2 pi f0 tau. But then we know how to take the Fourier transform of cosine functions. Remember that the cosine function in the frequency domain consists of 2 impulses. One is at f0, the other one is at minus f0. It's symmetric. And impulses have a strand 1 over 2 from now on in our new notation with f. So if we just remember this, we would have a squared over 2, but then another 1 over 2 term coming from the expression of the cosine, which makes a squared over 4, and then we would just write down the impulses. The first impulse at f0, and the second impulse at minus f0. So we could draw this power spectral density as a function of f. So one impulse at f0, another impulse at minus f0, and the strands of the impulses are a squared over 4 for both. Now we are asked to inspect some of the properties of the power spectral density. But first of all, we saw that in the last lecture we saw that For any random process, no matter if it's real or complex, the power spectral density always has two certain properties for sure. So it's always going to be real, as x of f cannot be a complex function. Remember, usually the Fourier transform of causal signals could be complex valued, but in this case, the Fourier transform of the autocorrelation function in particular cannot be complex valued. This is a particular case. So it's real, and it's always non-negative. A power spectral density cannot fall below zero. It cannot take a negative value, which totally makes sense because power is something positive by nature. So we already confirm these two properties. So we see that it's a real function, no complex values. And it is non-negative, it's always above 0. For this particular case, we can also observe that Sx of f has a certain symmetry, so it's an even function. It's symmetric with respect to the origin. So it's an even function, and if you remember, this case occurs here because of our particular situation that the random process is real valued. Remember, our random process is just a cosine function with some real amplitude, nothing imaginary in its expression. So the power spectral density is even because the our random process is real valued. So this was just a summary of some of the properties we saw last time. Now, if you look at the composition, well, if somebody just gave you this plot, the power spectral density, would you be able to tell the AC power, DC power, and the average power? Well, DC power, to find out the DC power, if you know that your process is ergodic, you look whether there's an impulse at f equals 0. In this case, there is not. Well, this arrow just denotes the name of the y-axis, so there's no impulse at f equals 0. So no impulse at f equals 0. So DC power is actually equal to 0. Then the average power, which is normally DC power plus the AC power, is completely equal to the AC power in this case. And then what is the average power? Well, you can immediately say the average power by looking at this plot, but because you have to just integrate the PSD between minus infinity and plus infinity, but then you only have two impulses, so the integral would be just the sums of the strengths of these impulses. So a squared over 4 plus a squared over 4, which gives you a squared over 2. So this is the average power of the random process. You could actually confirm the same thing. Remember, average power is very simply Rx of tau evaluated at tau equals 0. So you put 0 here, you would get the average power as a squared over 2. And this does not have a constant term. It only has a term varying with tau, which would correspond to Cx of tau. So the plus eta x squared part would be 0. We already see that eta x is 0 actually. So by this means, you could also conclude the expressions for the AC power, DC power, and average power. Okay, now our next exercise is very similar. Instead of a cosine, now we have a complex exponential. So let's see. So here in our random process has this form. So some complex exponential term which has deterministic frequency multiplied with a, but then a has a constant amplitude beta and a random phase term. So actually this random process is a complex exponential with a deterministic constant amplitude, deterministic constant function, and a random phase term. And the phase is uniformly distributed between 0 and 2 pi. Actually, in a previous exercise, we looked at this process. We showed that it is White-Sands stationary. We also showed that this process is ergodic, and the mean is 0, and the autocorrelation function is given by this expression. It depends on tau. Okay, now what we should do here is to look at the power spectral density of the process, and again, similarly, inspect some of the properties. So very simply, we're going to take the Fourier transform of the autocorrelation function to find the power spectral density. So Sx of f is the Fourier transform of Rx of tau. So Rx of tau is this expression, beta square times the complex exponential. The beta square might go out of the Fourier transform, and we will be left with the Fourier transform of the this complex exponential. So e to the j 2 pi f0 tau. Well, we saw how to take the Fourier transform of complex exponential. Actually, a complex exponential, a pure complex exponential with frequency f0 just corresponds to an impulse at f equals f0. So we know that the Fourier transform can be evaluated as, well, this beta square is a constant term, and the Fourier transform of the complex exponential should be an impulse delta located at f0. So we could also draw the PSD just to visualize. So it's a very simple PSD that consists of a single impulse at f0 with strength beta square. Now let's again look at some properties of the power spectral density. So the power spectral density should always be real valued. We check whether this holds. It holds, so it's real valued. This should always hold for any random process, no matter complex or real valued. It's also non-negative. It does not fall below 0. Notice that it could be 0 at some frequency. Actually, at all these frequencies, the PSD is 0 here. And then when it comes to the symmetry of the power spectral density, we see that in this case the PSD is not symmetric. It's not an even function. So it's not even. But then actually this is not surprising. Now if you come back to the random process we are dealing with, the random process is complex valued, right? There's a complex exponential in it. So when the process is complex valued, the symmetry property does not hold. So this is quite natural because x of t is not complex. When the process is real, like in the previous example, if you had an impulse, you would need to have an impulse at the symmetric point at minus f0. Okay, now we could also comment about the average power, AC power, and the DC power. So looking at the PSD of this random process, what is the DC power of this random process? Let's first find it out. We look at, very simply, we look what happens at f equals 0. Is there an impulse at f equals 0? So there is no impulse at f equals 0. So the DC power is equal to 0. So that the average power is going to be equal to the AC power. So the average power, we can simplify it by integrating Sx of f from minus infinity to plus infinity. So you're just integrating a single impulse function. And then the integral will be the strength of the impulse, which is beta square. So very simply, we can find out what the average power is, what the AC power is, what the DC power is. Okay, so this was also a simple exercise. There's just this remark relating this example to the previous one if you look at it. So let's switch to the next example. Now, in this case, we are actually not given the expression for the random process. We are not also told about the autocorrelation function. The only thing we know is the power spectral density. So we're given the expression of the power spectral density. It actually consists of 3 impulses. And what we are asked to find is the average power of the random process, the AC power, DC power components, and also the autocorrelation function. Again, this is a very simple exercise. So for visualization, let's plot the power spectral density. So you have one impulse at f equals 0, and then 2 impulses at F0 and minus F0. So the impulse at F equals 0 has strength 4, and the other impulses have strength 3/2. So now we have a random process that does have an impulse at F equals 0. So if you look at what happens at F equals 0, so this red part is going to give you the DC power, and the remaining components of the power spectral density, which come from the green parts here and here. The green parts are going to give you the AC power, actually. So this red part is DC, and the other components are going to be related to the AC power. So very simply, again, we could just decide the DC. Oops. We could just determine the DC power of the process. We just have to, well, formally speaking, how to write this, we just have to integrate, find the strength of the impulse at F equals 0. So mathematically, you could write this as integral from 0 minus to 0 plus the power spectral density dF. So just actually extracting the strength of this impulse with this integral, so it comes out as 4. And the average power would be the integral of the whole power spectral density on the whole real line, F line. So as x of f df from minus infinity to plus infinity. So when you do this integral, you're integrating over all these 3 impulses. So the integral will come out as 3/2 plus 4 plus 3/2, which makes 7. And then the AC power, you could actually find this immediately by integrating Sx of f over all f values other than f equals 0. So then you would be integrating this impulse and that one. So the AC power would be 3/2 plus 3/2, so 3. But formally speaking, you could mathematically write this as this is always equal to average power minus the DC power. So 7 minus 4, you have the same result as 3. Okay, now we also should find the autocorrelation function from this based on the power spectral density. So our x of tau, maybe switch to a new page. So our x of tau is, you should just take the inverse Fourier transform as x of f. But then this function is quite easy to invert. Why? Well, it has this constant impulse at f equals 0, the impulse at f equals 0, which corresponds to the constant value 4, right? And then the remaining terms, you have 2 impulses here that are symmetric at f0 and minus f0. They have the same strength. So we know that whenever this is the case, it should be related to a cosine function. So a cosine function would have amplitude 1/2, 1/2. So this is multiplied by a factor of 3. So we get this as 3 cosine 2 pi f0t. So from the 2 symmetric impulses, you have 3 cosine 2 pi f0 tau. And then from the impulse at f equals 0, you have the constant term 4. And remember, recall that this actually gives us the composition of the autocorrelation function in terms of the autocovariance function and eta x squared. So actually, we also know that nobody gave us the process in the first place, but by looking at the decomposition of this autocorrelation function, we know that the mean value of the random process should be, well, its square is 4, so the mean of the function of the random process should be equal to 2. Okay. Now, here are a couple of more, well, these were the simple exercises, warm-up exercises. So here is a more elaborate exercise on continuous time random processes. So here we have a random process that's wide sense stationary and also ergodic. And its autocorrelation function is given in this form. It's some function of tau. Actually, we have already studied this random process. It was before the virus break. We actually looked at some example where you have we called it the random binary wave. So the thing is, actually, we had a random process was like a square wave with amplitude A or minus A, but of course the value at each time slot could be randomly A or minus. It's something that like a square wave, so random binary wave. But then we introduced some delay to this random process, and then we looked at the properties of the random process. So I would just like to remind you the the corresponding random process we studied earlier in class. So let's recall this random process. So actually there were two versions of this example. I don't know if you remember. I guess we solved these two in all sections. So one version was without any delay. So we first looked at this one. So I'm just drawing one realization of the random process. So you had these time slots, t, 2t, 3t, and so on. And at each time slot, the random process could take the value a or minus a. So if you're sending a 1 as a bit, you have a. If you're sending 0 as your bit, it takes the value minus a. So a typical realization might look like this. If you're sending 1, 0, 1, 1, this is going to be the corresponding realization. So this was our random process, the original random process. So we looked at this random process. Actually, we studied whether this is White-Sands stationary, and it failed to be White-Sands stationary. Why? Even if you take the same tau, if your T1 and T2 are in the same interval, the ACF is something. But if T1 is here, T2 is here, so corresponding to different time intervals, and the ACF is something else. So this first process was not White-Sands stationary. And then what we did was we introduced some random delay to this random process. So we delayed this by some amount, random amount d. So d would just be something randomly distributed, uniform distributed between 0 and t. So that the delayed version of the random process would look like this. By the way, just to make this example well-defined between 0 and, well, this is going to be d. Random delay. Well, to make the process well-defined, I just made a slight modification in the notes. The original random process, I just changed to vary, to be defined from minus infinity to plus infinity. So if you just look at your notes, the first, I should start from minus infinity, not from 0, if you printed them last week. Otherwise, it's okay. Okay, now this red random process, we call it as x of t now. X of t is the red one with random delay, and remember that the delay is uniformly distributed between 0 and t. Now we studied this random process in class. We showed that although the black process is not White-Sands stationary, the red one is. The philosophy was something like the following. When studying the black process, depends depending on where T1 and T2 are chosen, the ACF changes. But then since we introduced a random delay, it could be anything between 0 and t. Now it doesn't matter anymore where you choose your T1 and T2. The ACF depends only on the time difference. This random delay somehow broke the dependence on where T1 and T2 are situated with respect to these time intervals 0 to 2t, 3t, and so on. Okay, so we showed that the ACF, now the red one is White-Sands stationary, so we can talk about its autocorrelation function as a function of tau. So the ACF, we obtained the expression for it. I think the derivations were a bit lengthy, but at the end we obtained that Rx of tau should have this triangular shape, and the peak value has amplitude a squared. Now, if you compare the expression in this question, this Rx of tau that you see here, the expression that you see here is the same as the autocorrelation function we saw earlier. Okay, so very well. Now, what we are asked to do here is to find the power spectral density of this random process. Now, obviously, what we have to do is we have to take the ACF and we have to take its Fourier transform. Now, if you think about this, this waveform as a function of tau, it has this, well, you see the shape here is something triangular. You could also write it in an open way as an explicit function of tau in this way. But, well, you could just apply the formula for the Fourier transform, multiply with a complex exponential integrate and so on, which is possible to do. But it would take some time. The derivations would be a bit lengthy. Now, the trick here, we will actually solve this example without any calculations at all. The trick will be to use the properties of the Fourier transform. So, if you stare at this function, and if I ask you to tell me a type of function, a kind of waveform, so that when I convolve it with itself, it should give me this triangular shape, triangular function. Now, what is that function? It's going to be rect, right? So let's try to write Rx of tau as the convolution of two rectangular functions. That's going to be very easy to take its Fourier transform, because when you take the Fourier transform of something convolved with something, you just have the Fourier transforms and then multiply them. Convolution in time domain corresponds to multiplication in the frequency domain. This is this very basic property. Now, the rest of the job is to write this as the convolution of two rectangles. But then there are some annoying things here, right? So it's from minus t to t, and there's some amplitude. We don't know the exact expression for that, but never mind. So let's take it easy. So let's get there from the other side. So if I take a rect function, a standard rect of tau, what was it again? If you don't have any scaling here, the scaling is 1. It means that the width of your rectangle should be 1. Always centered at 0 with our notation. So you simply have this box function from tau from minus 1 over 2 to 1 over 2. And then no amplitude here, so it's 1. So this is the rect function. Now, if I take it and convolve it itself, let's just redraw the same function in here. So what am I going to get? I know that I should get a triangular function. So where should be the center value of the triangle? Let's think about it. What is going to be the peak? Where is going to be the peak of the convolution? Well, the maximum overlap between these two functions will occur. Remember, in convolution, I take the second one, I time reverse the second one, and I slide it through the first one. The peak value of the convolution will occur, the maximum overlap will occur if I don't shift at all. So for the shift tau equals 0, I will have the peak value of the triangle. So my triangle is actually going to be symmetric. And what about the end values of the triangle? Well, the end point in here, again, one trick from the convolution. The end value in here will be the sum of the end values here and here. So 1 over 2 plus 1 over 2 is going to make 1. Similarly, the other end value would be minus 1. And what about the amplitude at the peak value? Well, then you should just look at the functions that you call those. At the peak value, I'm multiplying this first one with the other one. Time reversed, not shifted actually itself because of the symmetry. So 1 times 1, you're integrating 1 over this width of length 1. So 1 times 1, you get 1. So this is some other function of tau obtained by convolving these two rectangles. Well, let's give this triangular function a name. Let's call it g of tau, for example. What we know is that the Fourier transform of g of tau, we we can actually write it immediately. I know that convolution in time domain is multiplication of frequency domain, so I just have to take the Fourier transform of the rect. But then after we did the notation change, now rect of t maps to sinc of f. No normalization, no constants, nothing. So this is going to be sinc of f, but then multiply another sinc coming from here, so we're going to get sinc square of f. Now, this is very fine. Now, if you go back to the original example, actually we have to take the Fourier transform of this triangular function. Now, how to obtain the Fourier transform of this? We're lazy, we don't want to calculate anything. Now that we know the Fourier transform of g of tau. Well, if you can take g of tau and then play with the scale and multiply with amplitude and so on, if you can convert it to this one, then you're done. You can use the scaling property. So the only thing that's practical to know is the scaling property actually. So we are going to take this. We would like to convert it into that one. Well, you'll see that the value 1 here should map to t. Imagine that t is something big. You're actually stretching your triangular function, right? So if you just try to write Rx of tau in terms of gt, so we should stretch by t, so this corresponds to division by t, and then the amplitude 1 should be converted into a square, so it's very simply multiply with a square. So a square g of tau over t. Now, you can actually take the Fourier transform of both sides now. So as x of f, now we are actually trying to take the Fourier transform of this function, right? Well, we don't know the Fourier transform of this, but we know the Fourier transform of g of tau. Now, to convert g of tau to this, we have actually divided by t. Remember the scale property. If you divide by t in the time domain, you should multiply by t in the frequency domain. So you take the corresponding Fourier transform to sinc square of f, but then divide by t here, you should multiply by t in the f domain, so you get tf. But then for normalization, whatever you put here, you immediately stick it to the expression. This is a normalization property. And then the only thing you're left with is to take care of the amplitude. You just copy it, linearity of the Fourier transform. Very simply, we found the power spectral density of our random process. Now, the second part of the question asks us to find the average power. Well, one way to do it, you could actually integrate this between minus infinity and infinity, but this is the more complicated approach in this case. Very simply, how do you find the average power? The average power is immediately hidden in the expression of the ACF, so you just look at Rx of tau at tau equals 0, and this is equal to the average power, so which is a square in this case. Okay, so we now continue with some examples in discrete time. So let's first look at the equivalent equation relating the autocorrelation function and the autocovariance function in discrete time. So very simple to the continuous time case, you can find the following relation between Rx of m and Cx of m. Again, this simply comes from the definition of the autocovariance function for discrete time processes. Now, if you take the Fourier transform of both sides of this equation, and the Fourier transform of the autocorrelation function will be the power spectral density. So Cx of m, so we're talking about the dTFT here, by the way. So Cx of m will have some dTFTs just denoted like this in here. And finally, you have this constant term here, eta x squared, constant with respect to m. So if you take the dTFT of a constant function, so what will you have? You're going to have an impulse located at omega equals 0, right? So the strength of that impulse will be eta x squared. So because of the normalization factor, now we have to add this 2 pi constant in here. But then we just have to be careful about the periodicity of the DTFT. So since the DTFT is periodic in omega, it repeats itself every 2 pi in intervals of length 2 pi. So we have to extend this impulse at delta omega. This has to have a replica at 2 pi, 4 pi, 6 pi, minus 2 pi, and so on. So just put an infinite sum in here, and each value of k will repeat this impulse at a value like 2 pi, 4 pi, and so on. Okay, now actually when x of n is ergodic, we, like similarly to the continuous time case, we have a special interpretation of the power spectral density. So for ergodic processes, what you always have is that the autocovariance function will not have a DC offset. So the DC offset of the autocovariance function will be 0. What does this mean again? Some typical cases are Cx of m might have some oscillator behavior around the mean value 0, or in some cases Cx of m might have some transient behavior and converge to 0 as m goes to infinity. But Cx of m cannot converge to something other than 0. In other words, it cannot have a DC offset. Now, since this function Cx of m does not have a DC offset, when you look at the Fourier transform of Cx of m, you won't observe any impulse at omega equals 0. So this first term will not contain any impulses at the particular frequency 0 in the DTFT domain. So what this means is very similar to the continuous time case. When you inspect the PSD of a discrete time random process, you just look whether there's an impulse at omega equals 0, and then if there is an impulse present at omega equals 0, then you let the DC power is non-zero. So that impulse, the strength of that impulse corresponds to the DC power of the process. So very, very straightforward extension of what we saw for the continuous time random processes. All right, so let's now look at a couple of example questions. This first one is about a discrete time random process. So it's basically a cosine function with some deterministic amplitude A, some deterministic frequency omega 0, and some random phase. So only randomness comes from the phase, like we saw in some other examples. So the phase term is uniformly distributed between 0 and 2 pi. However, an important part of this feature about this problem is that the frequency omega 0 is a multiple of pi. So this actually ensures that the random process is periodic. Any realization of the random process is periodic. Just be careful when you look at a realization of this random process. Theta is just something. Just ignore it. Some phase term. The variation is coming from this part, omega 0 n. So in the case that omega 0 is not a multiple of pi, for instance, if omega 0 is 1, think about the function cosine n. Is this function periodic in n? The answer is no, it's not periodic. The values, you will observe some cycles, but the values will never repeat themselves. So it's not, technically speaking, it's not a periodic function. So, but if omega 0 is a constant, is a rational number times pi, then you know that cosine omega 0 n is periodic. And similar, if you just add a phase term, it's still going to be a periodic function. Okay, now let's look at the question. So in the first part, we are asked whether this random process is White-Sand stationary. So we should decide if it's White-Sand stationary, and if yes, we should find the power spectral density, and then we are also asked about the Z transform of the autocorrelation function. So let's look at this. So first of all, I would just like to draw a realization of this random process, good for understanding what will happen. So x of n is just some cosine function with a random phase. Just let's just draw one period of this random process. So something like this, let's say. So the phase is random, so it might start at some arbitrary time instant. So let's maybe just put some 0 arbitrarily in here. And then the period of the random process is n0. Okay, so this is just a typical realization of our random process. So now to decide whether x of n is White-Sands stationary or not, well, we should look at two things. We should first check whether the mean function is constant, and then we should check whether the ACF depends only on the time delay. So let's begin with the mean function. So the mean function eta x of n, this is equal to the expectation of our random process at each n value. So let's find this. So x of n is equal to a cosine omega 0 n plus some random theta. So here we have an expectation to evaluate. If you just pay attention here, what is random and what is deterministic in here? So A is a constant, deterministic. Well, omega 0 n term, it's time varying, but it's something deterministic, right? So the only thing that's random in here is theta. So when we evaluate this expectation, the only randoms comes from theta. So we should compute this expectation by integrating over the density of theta. So let's do that. This A factor might come out. So then we are evaluating the expectation of this cosine term. You should imagine the PDF of theta here. So theta is uniformly distributed between 0 and 2 pi. So I just write down the function whose expectation I am looking at. And then here I should write f theta of theta, the density, but it's uniformly distributed, so I just have 1 over 2 pi. And the integration is over theta. Now, okay, if you just look at what's happening here, so from the perspective of this integral, theta is our variable of integration, and this first term, omega 0 n, is something constant from the perspective of this integral, right? So actually, if you just think about it, you can simply regard this omega 0 n term as some phase term, and then here we have some cosine function of theta integrated over a period. So the period of cosine theta is 2 pi, integrating over one period, so this integral will come out as 0, and then we have that the expectation expression is equal to 0. So we have thus verified that this process is stationary in the mean. Why? The mean function does not have any dependence on n. It's a constant function, so we conclude that this process is stationary in the mean. Remember, we were trying to find whether the process is White-Sands stationary, so the next step is going to be to see whether the autocorrelation function depends only on the time difference. So let's do that part now. So we look at the autocorrelation function, looking at some time instant n plus m and n. So this is the expectation of x of n plus m multiplied with x of n conjugate, in case this is complex. Now let's just plug in the expressions for our random process. Now, so we are looking at the expectation of, so let's write x of n plus m, which is going to be a cosine omega 0 n plus m, and then the random phase value. And then you have x of n, it's real value, so you can ignore the complex conjugate. So this is going to be a cosine omega 0 n, so a is already here, so let's just put square. So a cosine omega 0 n, and the same phase value. Now, again, the randomness, the only randomness is in the theta term in here, so we should evaluate an expectation over theta. But then, to make our job easier now, we could just use the trigonometric identity. So if you just imagine, if you just name this first term inside the first cosine as a, like small a, so this will be cos a, and this one would be b. So you have cos a, cos b, this is the famous formula. cos A cos B, you have that is equal to cosine A plus B plus cosine A minus B, and the whole expression divided by 2. So let's use that trigonometric identity. So A squared will go outside, and we have this 1 over 2 factor coming from the trigonometric identity. And then let's rewrite our expectation operation. I haven't evaluated the expectation yet, I'm just reorganizing what's inside the expectation. So the first term will be from cosine A plus B, just summing up the arguments of the cosines, omega 0, okay, n plus m, and then 1n coming from here, so 2n plus m. And then you have theta plus theta, which makes 2 theta. So this is the A plus B term. And then you will have A minus B. So if you just look at here, this omega 0 n will cancel with that one. Theta will cancel with that one. So you will have cosine omega 0 n. Now we're looking at this expectation. Again, the randomness comes from theta. Now, imagine that it's actually very similar to the integral we just computed. To evaluate this expectation, you integrate over the density of theta. Now this term will simply be something like a constant phase term, and then you have 2 theta. So in the previous case, we had only 1 theta. So our function, periodic function of theta, would make only 1 cycle. Now here it just makes 2 cycles. The frequency is doubled. And obviously, since you're integrating this over the period 2 pi, again talking in terms of the theta variable, this expectation will come out as 0. Now, so this one will disappear when the expectation is evaluated, so you'll be left with the expectation of the second term. But then what is that? Well, theta is random. There is nothing about theta in here, it's just a constant term, so it just goes out as itself. So the result will be a squared over 2 times this second term, cosine omega 0 n. So this is the expectation that we found for the autocorrelation function. Now we started with n plus m and n, but then this expression does not depend on n, it only depends on m. So we can write this as the autocorrelation function of a single variable m, the time delay. So we know that if this property holds, we say that the process is stationary in the ACF. So our process is stationary in the mean. We found it here. It's stationary in the ACF. We conclude that our process is White-sense stationary. Now, in the second part of this question, well, we have shown this White-sense stationary. Now, the next thing to do is to find the power spectral density. Let's do that. So, power spectral density is, we will very simply take the DTFT of the autocorrelation function. Now, well, the autocorrelation function, we saw it to be a cosine function in here, right? A discrete time cosine function, which is periodic because omega 0 is pi times something. Now, the DTFT, if you evaluate the DTFT of this, you know that a cosine function can be written as a sum of 2 complex exponentials. One located at frequency omega 0, the other one at minus omega 0. So we could just write down the Fourier transform corresponding to this. So you have this a squared over 2 factor. Let's just copy it here. So when you write a cosine, exponential something plus exponential something divided by 2, so you have this 1 over 2 factor. But then you need to have a 2 pi factor for normalization. So 1 over 2 times 2 pi, it makes pi. Then we have to locate our impulses. So one impulse will be at omega 0, complex exponential of frequency omega 0. And then another impulse is going to be at minus omega 0. So theta plus omega plus omega 0. So I'll just maybe write it down there. So the equation would be as simple as this if we didn't have the periodicity issue. So we just have the sum of these two impulses. But now we know that DTFT must be periodic, so we have to make a periodic extension of these impulses. So you should repeat them every 2 pi frequencies. So how to do that? We just put an infinite sum. So k from minus infinity to infinity. And this impulse we will repeat every 2 pi frequency interval, so it makes k 2 pi k. And also that one we repeated every 2 pi k frequency intervals. So this is the expression that we obtain for the DTFT autocorrelation, DTFT of the autocorrelation function, so the power spectral density of this discrete time random process. We just observe that, observe the properties of this DTF of this power spectral density. It's a real function, it's non-negative, and it's also an even function because the impulses have this symmetry. Well, why is this even? Because just like we saw for the continuous time processes, the same property holds here too. This discrete time random process is real valued, so that its power spectral density is an even function of omega. And then you have this last part that asks about the Z transform of the autocorrelation function. Now let's think whether the whether Sx of z exists. So if we were to take the Z transform of the autocorrelation function, so let's write Rx of m, what would we have? We would have this infinite sum, so Rx of m z minus m, right? So m from minus infinity to plus infinity. So in this particular case, Rx of m is in the form of a cosine function, so it oscillates, it's periodic. Now, if you look at the convergence of this infinite sum, when you plug in a cosine in here, you will see that it will not converge. Why? How to see that? If you just break this sum into two terms, where you put in the negative terms in here, Rx of m, z minus m, and then let's also add the second term that's about that captures the non-negative terms, so from 0 up to infinity. So for this Z transform to exist, this first sum should converge, and the second sum should converge. But if you make this converges for what values of Z? This one will converge when the magnitude of Z is smaller than 1. And the second sum will converge for Z values that have magnitudes larger than 1. And if you intersect these two regions of convergence, you get empty set. So the region of convergence of this overall expression is the empty set. So this is why the Z transform does not exist. So Sx of Z does not exist. Just observe that the non-existence of the Z transform is somehow coherent with the strange form of the power spectral density we obtained in here. Well, we say that this exists. Well, we write the expression, but actually, technically speaking, this function is a very weird function with some impulses. So going to infinity as some certain frequency. So technically speaking, we would even say that the DTFT does not exist. But if we allow ourselves to use impulses, then we can talk about the DTFT. Okay. So actually, you can see that this the region of convergence being empty set, hence the conclusion that the Z transform does not exist, it's not limited to a cosine function. So if Rx of m is a periodic function in general, so if in general when you take the Z transform of a periodic function, you run into trouble because when the positive m terms converge, these don't converge, and when the for Z values where this negative part of the sum converges, the positive part will diverge. So you will never find an intersection. So periodic functions don't have Z transforms as a general rule. Okay. Now let's pass to this second part. So if x of n is ergodic, show it and find the average power. So we should check whether our random process is ergodic, And then if yes, we should find the average power. So part B. So to find that it's, to see whether it's ergodic or not, we should check. In general, if somebody asks you whether a process is ergodic, you should check two things. You should check ergodicity in the mean and ergodicity in the ACF. So if both of them are satisfied, you say that your process is ergodic. So let's first check ergodicity in the mean. So we should check this time average for our random process. So if you like denoting it in this way, it's fine. I like seeing this as an estimate of the mean of the random process. So I just put this. I like this notation. Well, when you see a hat, it means that you're estimating something. So just put this into some meaningful context. It doesn't matter. You can use whichever rotation you like. So the time average is obtained as follows. So we take an infinite sum. So we let n go to infinity. We sum up all the observations, all the samples from our random process from n0 up to n-1 with the normalization. So just write down the values of the samples here. So our process is a cosine omega 0 n plus theta. Okay. Now, you could try to evaluate this infinite sum, but if you just realize that, let's remember that our process is, any realization of our process is periodic. So actually, what you're doing is you're summing up all these values and then averaging. But then repeating this over infinitely many periods, you will just get the same thing that you will obtain if you did the averaging over a single period, right? So because of the periodicity of this random process, you could just simplify your work and you would say that no need to go into infinite sums. I can just do this time averaging over a single period. It will be enough. So remember that the period of the random process is given as n0. So summation from 0 up to n0 minus 1. Omega 0 n cosine omega 0 n plus theta. Now again, we should remember here that we're looking at the time average over a single realization of the random process. Again, any realization looks like this. So you're summing it up over a single period. So in any realization, you have some random theta value. The process could start anywhere, but if you're focusing on a single fixed realization, theta will just have some value and it will be fixed throughout that realization. So now, once we notice this, we realize that we could simply ignore this theta term. You could actually think of this as something fixed. You can erase this theta, erase this tilde sign here if you feel more comfortable. This is a constant of phase term since we have fixed the realization. And what we are doing here is we are time averaging. So n is the variable that runs through this time, through this process. So you're actually adding up the samples of a cosine function over a period, over a complete whole period. So this is going to be 0, right? So this is going to add up to 0. And the critical thing is that this is 0 for any realization of the random process. So for any value of theta, I will get 0. So any realization meaning that any theta. Theta is treated as something fixed when we are looking at a single realization of our random process. Okay, so since this sum is equal to 0, then the time average estimate of the mean is found as 0, but then it's equal to its actual value. So the true value of the time of the mean of our random process was 0. So it's equal to its time average estimate. So since the time average is equal to the expectation, then we conclude that this process is ergodic in the mean. Or simply, you can call it mean ergodic. Now, to solve the rest of the question, we have to look whether it's also ergodic in the ACF. So To do that, we look at the time average estimate of the autocorrelation function. So our x of m, I'm just insisting on the hat sign, so it's a time average estimate. If this is confusing you, never mind, just use this notation. We're looking at this expression, x of n plus m, x of n, and the brackets mean that you're taking average over time. And we will see whether this comes out to be equal to the autocorrelation function itself. So let's write down the expression for the the time average calculation. So n goes to infinity, normalization with n. So small n should run up from 0 up to n minus 1. So I'm just writing down the expression for the random process a cosine omega 0 n plus m plus theta. Again, this theta, we are taking a single realization, taking the average over time, so this theta is, this has a fixed value throughout the whole summation over n. So this thing multiplied with, I'm just continuing here, the second term, x hat of n, x conjugate of n, but they are real values, so x of n, omega 0 n plus theta, and these are multiplied. Now we can simplify this expression further. Now, first of all, realize that when your random process is periodic, this time average estimate regarded as a function, well, this expression of n is also going to be periodic in time. So you could just do the summation over a single period. No need to go into the infinite sums in here. So you could just simplify the expression by just getting rid of all the limits and everything and doing the same exact summation over a single period. So n from 0 up to n0 minus 1. And then we could again work a little bit on these terms. So this here you will see a squared, a times a. And then you have some expression in the form cos a times cos b. You could again apply the trigonometric identity. So let's just write down the cosine a plus b term. So I'm just summing up the inside of the first cosine with the inside of the second cosine. So you'll get 2 omega 0 n, one from here, plus some 1 omega 0 m coming from here. And then you have 1 theta, 2 thetas. So this is going to be the first term. And then you will have the cosine a minus b term. Let's write it as a separate sum. Just repeating the overheads. So a squared. So this time we will write cosine a minus b, which will be, well, this omega 0 m will cancel with that one. So omega 0 m, and then theta will cancel with that one. So that's all we have. So okay, I guess I just forgot cosine a cosine b is equal to 1 over 2 times the rest of the expression. So we should just put the the 1 over 2 factors in here. Okay, now if you look into these sums, again, this is a time average over a single realization. You could treat this theta as something fixed throughout that realization of the random process. So this is a constant phase term, m is, these two terms, you can just think of them as a constant phase term. The variation is with respect to n. And then you have a cosine function that completes 2 cycles because of this 2 factor. That completes 2 cycles within a single period. So when you sum up the values of this cosine function, we get 0, right? And then you're left with the second term. But then this second term does not depend on n. So we have a summation over n, and we're averaging. So this constant term will just come out as itself. So the answer will be a squared over 2 cosine omega 0 m. Okay, now this was the time average estimate of the autocorrelation function. Now to find out whether the process is ergodic or not, we should compare this expression to the true autocorrelation function. But the autocorrelation function was found here as a squared over 2 cosine omega 0 m. Now comparing the expressions, we see that we have the same expression. So this is equal to the true autocorrelation function Rx of n. So since the autocorrelation function is equal to its time estimate, we conclude that our process is stationary, ergodic in the ACF. We could simply write it as ACF ergodic. Now, since we were asked whether the process was ergodic, we verified that it's mean ergodic, and now we saw that it's ACF ergodic, so we conclude that the process, this random process x of n, is an ergodic random process. So we are then asked to find the average power of the random process, but this is very, very simple. You just look at the autocorrelation function, you just evaluate this at m equals 0, you'll simply get a square over 2. So the average power of the random process is Rx evaluated at 0. So this is a square over 2. Okay, so this will be the solution to this first example. And then we have a second example. Well, this example is kind of lengthy. I think it's a very good one. It's kind of a more profound example. So if you're short of time, you could actually skip this one for the moment. It's not very, very critical. Although it would be good to come back to it and study it later on. If you have time and patience, you can just go through it together. But I like this one very much. So it's actually, the idea here is to show that Bernoulli processes are ergodic. So actually looking at the solution of this example, we will gain some further insight into the concept of ergodicity. So let's go through this. So let's first study what this question tells us. Here we have a Bernoulli process. Remember that Bernoulli processes have independent, identically distributed samples. So at each n value, the value of the process is equal to some different random variable an. And all these random variables an are Bernoulli random variables. It means that they are either 0 or 1. They are 1 with probability p and 0 with probability 1 minus p. And all the samples are independent and identically distributed. They all have the same distribution, Bernoulli distribution, and each sample is independent of the other samples. So I guess in a previous exercise in class, we showed that the Bernoulli processes are not only wide sense stationary, but they're also strict sense stationary. Actually, we showed that they were n order stationary for each n, so it followed that they are strict sense stationary. So we also found that the mean function of the Bernoulli process is equal to p, simply the expectation of each sample, 1 with probability p, 0 with probability 1 minus p, so expectation comes out as p. And also it's simple, very, very easy to show that the autocorrelation function of the random process is given by this expression. Now, this question has 5 parts. And the first part is the longest and technically deepest part, but I like this very much. So we're here asked to show that the random process is ergodic. Now this question is actually a difficult one. Why? Well, let's look at what we did so far. So very simply, this wasn't ergodicity wasn't hard to show in the previous examples. For instance, remember the previous example, what did we do here? We looked at the single realization of the process. Think about ergodicity in the mean. So you're looking at the time average of the samples. So you're basically summing up all the values of the process for different n values and then dividing by n. But what we had in the previous examples is that throughout the same realization of the process, the randomness was actually removed because theta had a certain fixed value. So it was quite easy to do the maths to find the time averages. Theta was fixed, we treated as a constant phase term, and then the summations were easy to make. Here we have the situation is different by its nature here. what happens here when you look at the time average of a single realization of this random process is that you have to take into account many different random variables. So if we just draw let's just draw a realization of our random process. So our random process will be something like, so values at 0, 1, 2, and so on. So n. So it's either 1 or 0, so maybe it might be 1 here, 0, 0, 1, 1, 0, and so on. So when you look at the time average of this random process, what are you doing? You're taking this random variable, and that one, and that one, and that one, and then summing up all these random variables. So you have a summation of many different random, infinitely many different random variables actually. And then you're wondering, to check whether the process is mean or ergodic, you're wondering whether this summation of infinitely many random variables converges to something. So actually this issue is quite technical. We're going into a stochastic convergence issue here. So we should check whether a summation or sequence of random variables converges to a constant value or something. This is not quite easy. So yeah, I hope you understand the difference in the nature of this problem and the previous one. So each term is independent of each other. They are all random variables in here, whereas in the previous cosine example, once we fixed the realization, everything was deterministic. This is why this question is a bit difficult. So now, without having to go into those stochastic convergence considerations, what I propose is the following hint to solve this exercise very simply. So let's look at what this hint tells us. A sufficient condition for a White-Sun stationary random process to be mean ergodic is that the autocovariance function converges to 0 as m goes to infinity. So we should read this statement in the correct way. It says the following. You have a random process, you're wondering whether it's ergodic. If somehow you manage to show that the autocovariance function decays to 0 as m increases, then you're fine. You're sure that your process is ergodic. You don't have to look at anything else. However, this is a sufficient condition. It's not a necessary condition, which means the following. You might have some processes where the autocovariance function does not converge to 0, but your process might still be ergodic. Just look at the many examples we had with, like in here, for instance, the autocorrelation function was oscillating, so the autocovariance function also oscillated, but the processes were still ergodic. So it's not a necessary condition, this is a sufficient condition. But in this case, we will see that this sufficient condition will hold, and then we will thus see that our process is ergodic. However, be careful, this is a sufficient condition only for the mean ergodicity. So now let's look into the details of this. But what I would first like to do is I would like to give you some intuition about this hint. Actually, in some textbooks, this statement is presented as a theorem. It's called the mean ergodic theorem. I don't want to go into rigorous things and make a proof, and so, which is possible, by the way, technical but easy to do. I don't want to prove anything, but I would just like to give you some intuition about why the autocovariance function converging to 0 gives you the ergodicity. So to see that, just a very little intuition about why this is the case. Imagine that somebody, let's forget about the example random process we have now. Let's think about an arbitrary random process, and we are looking at the autocovariance function of some random process plotted with respect to m. So imagine that the autocovariance function converges to 0 as m increases. Now, so typically you would have some decaying behavior as m increases. But what you have here, what does this m decreasing to 0 actually mean? The value in here, looking at it at some large m, you're talking about the autocovariance function, so the value in here is nothing but the covariance of these two random variables. You're looking at x of n plus m and x of n. Well, this is the definition of the autocovariance function, right? So if you want to relate this to the original random process, I'm just talking about an arbitrary random process in here. So I'm just drawing some random process x of n. So let's say that we have some sample x of n in here. And then you're wondering what happens for very large m, right? So I'm looking at the same random process some time later, but a large amount of time later, so large m. I'm looking at a sample very, very further away. So I have some sample n plus m here. So here is the sample x of n plus m, just for visualizing what this means. So for a random process, if Cx of m converges to 0, it means that this covariance, so the covariance between this random variable and that random variable, as you increase the time difference between them, as you increase m, the covariance of these two random variables will converge to 0. It will become smaller and smaller, which intuitively means that these two random variables become less correlated. Intuitively speaking, again, what this tells you about your random process is following. So suppose you're trying to find the mean average, you're trying to estimate the mean of your random process by looking at the time average. So what you do is you take this sample, sum it up, you keep summing up over the over different n values. So and this is an infinite sum. You're actually running this sum from 0 up to infinity. So if this covariance function is close to 0 for large n, it means that this sample and this sample are more and more uncorrelated, meaning that their information content, their common information content, gets weaker and weaker as m increases, which is actually a good thing, because this random variable not being correlated with this one means that when you add the information of this new random variable to your infinite sum, to your time average, this will bring some new information that was not in the past samples. So even if you fix a single realization, each time you add a new sample, you gain new information, extra information about the statistics of your random process, meaning that the covariance function converging to 0, if this is the case for a random process, because of the extra information you gain from each sample, the time average estimate of the mean will be an accurate one, because with each sample you're gaining new information, and in the limit, the time average estimate will give you the correct value of the mean of your random process. This is the idea. So kind of each sample, covariance decaying to 0 means that each sample brings some new innovation, some new information into your estimate of the mean of your random process. So if this is confusing for you, never mind. All we have to do here to solve this question is we should look whether to find the mean ergocity, we should look at the autocovariance function, and we should check whether it goes to 0 or not as m goes to infinity. So so let's do that. So to solve the first part, let's just find out the expression for the autocovariance function. So we know how this is related to the autocorrelation function. So this is Rx of m minus eta x squared. Remember, our process is Weissen's stationary. So this is equal to p squared. It's actually given in the question. Mean is equal to p, and the autocorrelation function has this expression. So when you subtract eta x squared, this term disappears, so you're left with this term. So let's write it down. So this is p of 1, p times 1 minus p. We could just simply rewrite as p minus p squared delta m, and that's it. Now we're wondering, again, to check ergodicity, we're wondering whether this function converges to 0 for large m. But then if you just look at what this function looks like, it's a very, very simple function. At 0, you have the value p minus p squared, and at all the other values, this function is actually exactly equal to 0. So this is what the autocovariance function of this random process looks like. It's always 0. Now, if I ask you whether this function converges to 0 as m goes to infinity, the answer is obviously, trivially, yes. So Cox of M is actually not converging to 0, it's exactly equal to 0 for large M. So again, going back to the hint, this doesn't have to be the case for any ergodic random process, but the moment where you verify that your random process has this property, you know that it's ergodic. So from this condition, we can immediately say that x of n is ergodic in the mean. Is mean ergodic, let's write. Now, this first part is fine. The next thing we have to do is to check whether the autocovariance function also has this property. So we should check whether the process is ACF ergodic. Now we will see that this is going to be somewhat more involved than the mean ergodicity, but let's see. Let's go there step by step. So to check the ACF ergodicity, you can use either notation. So we're looking at the time average estimate of the autocorrelation function. So this is the expression we have to compute. Let's take it easy and let's write down what this looks like. So we're having an infinite sum here. N goes to infinity 1 over n. And the time average estimate of this expression, x of n plus m, x of n. Okay, now the story is getting a little bit complicated here, but if we just go through the steps carefully, we can make it. Now the trick will be the following. What I will do is, from now on, I want to actually relieve my mind. So my first immediate question is whether this expression of m is equal to the actual autocorrelation function Rxm. If I can show that this holds for any arbitrary m, then I'm done. But for showing this, what we will do is we will fix m first to relieve our minds. So fix m. Now from now on, m is something fixed. For instance, m is equal to 2. So we fix it. Now I'm fixing m, and then I'm looking at what I have in this sum. So you have to samples from your random process multiply with each other. M is fixed, so I don't care about the dependence on m. I'm looking at this thing as something that changes with n. I could actually give this another name. So I could see this as a new random process. Let me call it as v tilde of n. So this is a new random process. I won't go into the details, but it's easy to show that this is a wide sense stationary random process. You could ask whether it's ergodic or not. The question is valid. Now let's see. For fixed m, so I'm insisting on this. So for fixed m, let's see what this expression gives us. So we're looking at the time average estimate. I will just rewrite this sum in terms of our new random process. So what we have is an infinite sum, n goes to infinity. So n from 0 up to n minus 1. Now I will actually replace this expression. Now I will simply call this as v hat of n. I will write it in terms of my new random process. Now m is fixed. We're just wondering whether this is equal to the autocorrelation function evaluated at m. If yes, then we'll conclude the process is ergodic in the ACF. But now what this is in terms of, from the perspective of the new random process Vn, this is, what is this? You're taking samples from Vn, adding them up, averaging over time. This is the time average estimate of the mean of this new random process, right? So we could actually rewrite this thing as v of n, the time average estimate, or if you prefer the other notation, this is the estimate of the mean value of the random process. Now the big question is whether this, we don't know yet if Vn is an ergodic process or not. So we're wondering whether this time average estimate is actually equal to the true mean of the random process Vn. We don't know yet whether this occurs or not. But let's first maybe see what the eta V would be. So we don't know if this is equal to time average estimate, but let's just, by curiosity, find out what's the mean of this new function. So the expectation of V of n. So this is x of n plus m, x conjugate of n. This just simply comes from the definition of V of n. But then what is this expression? Does this ring a bell? Looking at this expectation. Well, this is nothing but the autocorrelation function of our original random process, right? So this is equal to Rx of m. Now again, wrapping it up, what we have is this estimate, time average estimate of the ACF, is equal to the time average estimate of the new random process V. Now we don't know if the random process V is ergodic, but if somehow we manage to show that V is ergodic, we know that this time average is equal to this. If V is ergodic, we have that property. But then what do we have? If that equality holds, just imagine that you're wondering whether this equation is equal to the expressions in the previous page. So if this equality, if we can confirm this equality, we will have that the time average estimate of the ACF of x, we just follow all these equalities, so it will be equal to the true autocorrelation function. So the only question we have to answer here is whether this new random process is mean ergodic or not. If this is mean ergodic, then we're done. We have shown that x is ergodic in the ACF. So let's check whether V is mean ergodic now. Again, the trick will be to simply look at the autocovariance function of V of n. So let's check. Again, we're in a setting where we have fixed m. M is our special variable that we reserve for this situation. Now, if you just pick another dummy variable, so we are wondering whether the autocovariance function of V, let's just put k here now, whether this thing converges to 0 or not as k goes to infinity. So, but this is actually not quite difficult. So I will just provide an intuitive answer to that. So this is, first of all, the covariance of these two random variables. We look at V at n plus k, and now we look at V at n, and we're interested in nothing but the covariance of these two random variables, right? So what we have here is, well, let's just visualize. Visualization is sometimes much more powerful than struggling with equations. I'll just draw a realization of my original random process here. So this is x of n, some realization from x of n. So it takes some value, 0 or 1. Let's say that it took the value, some certain value at n. And let's look at what these random variables intuitively mean. Remember, what was the definition of V? V of n is nothing but these random variables. M is fixed, never mind, m is equal to 2. V of n is this product. So let's look at what this visually corresponds to. I'm looking at the product of x of n and x of n plus m. M is some certain number. So I just take a certain time delay starting from n. So I have this new random variable. So V of n will be nothing but the product of these two random variables. I could simply call this product. Arrows will indicate the product here. This is V of n. So this random variable. Then I have V of n plus k. Means that I will do the same thing, but I won't start with n. I will do the same thing at n plus k. So let's do that. So our random process continues. So I go up to n plus k, some sample n plus k, and then I do the same thing. I look at the process just m samples later. So I look at these two random variables, the product of these two random variables. And the product of these two random variables will be nothing but we evaluated at n plus k. Now my question for you is the following. What is this covariance? Now here we have the liberty to take k as much as we want. So you could increase this separation as much as you want because we're interested in what happens to this for very large k. Actually, we're looking at it as k goes to infinity. So m is some certain variable, but whatever m is, we don't mind. We can make k as large as we want. My question is, take k as large as you want. What will be this covariance in the limit? Now the answer is, look whether these random variables are dependent, the red ones. Are these two red random variables dependent or not? So v of n depends on this value and this value of x. V of n plus k depends on this one and this one. But the nice property that the Bernoulli process has is that all the samples of x of n are independent of each other. So v of n depending on these two only, and v of n plus k depending on completely different samples from x of n, means that v of n and v of n plus k, so the red random variables, the two red random variables, they are independent of each other. This simply concludes that their covariance is equal to 0 if I choose k as large as I want. So for, let's say, for k large enough. It just simply follows from the special property of Bernoulli processes that each sample is independent of the other samples. So from here, what we conclude is the following. So for k large enough, so for each fixed m, let's gather up what we have. So for each fixed m, we have that Cv of k is equal to 0 as k goes to infinity, from which we conclude that there's an implication here. This implies that our new random process Vn is mean ergodic. Remember, this was what was given on the hint, right? Look at the autocovariance. If it converges to 0, then you're fine. Your process is mean ergodic. We just use this property for, not for x, but for v in here. But then back to our reasoning here. So following all these chains of equalities, now we have just concluded this last equality. So v is mean ergodic, so the time average estimate of the mean is really equal to the mean function. So we have actually confirmed that this equality holds. But then since this equality is confirmed, now we conclude that the time average estimate of the ACF of x, which is here, is equal to the actual the true autocorrelation function. So from here we conclude that the random process x of n is ergodic in the ACF. In particular, for each fixed n, for each fixed m, we have shown this equality, time average estimate, being equal to the true autocorrelation function. So since this holds for each finite fixed m value, now we know that the process x is ergodic in the ACF. So this was a long example, but what we have done so far to wrap up is we use this, actually it's simple. We use this hint to first show that x of n is ergodic in the mean, and then to show that x of n is ergodic in the ACF, we played with the expressions a little bit, created a new random process, showed that that random process is mean ergodic, still using the same property, which eventually implied that x of n is also ergodic in the ACF. So being mean ergodic and ACF ergodic, x of n is an ergodic random process. So this was a rigorous proof of the ergodicity of x of n. Now, in the next question, we are don't worry, the rest of the question, rest of the question is going to be shorter. So we are asked to find the power spectral density and the average power of x of n and find the AC/DC power proportions. Let's do this. Now, we are actually quite relaxed here. Why? We have already found the, well, it's not actually here, it's even here. We have the expression for the autocorrelation function of the random process. We just have to take its Fourier transform. So this is part B. So Rx of m, I'll just write down the expression P1 minus P delta m plus P squared. Just recognizing these different terms as we just saw in here, this is going to be the DC term, so the term corresponding to eta x squared. And this is the, if we might call it, the AC term, so Cx of m. So it's then immediate to know that the average power is obtained by evaluating the ACF at m equals 0. So just putting m equals 0 here, you have p times 1 minus p, and then p squared. So this term is going to be the AC power. And the second term, since it comes from the constant term, is going to be the DC power. If you take the Fourier transform of Rx of m now, you obtain the power spectral density as x of e to the j omega. Remember, we are taking the dTFT here. So you have an impulse at m equals 0. Impulse, the dTFT of an impulse is the constant function, so simply comes out as the constant term p times 1 minus p. And then you have this constant term. You know that by the duality, if you have a constant in your signal, then in the Fourier domain it's going to be an impulse located at the frequency omega equals 0. So we repeat the amplitude, copy the amplitude. You have this 2 pi factor for normalization, and then you would normally have a delta at omega equals to 0. But then, since it's periodic, we just have to make this periodic by introducing an infinite sum. So, k from minus infinity to infinity, omega minus k2 pi. So this is the expression for the power spectral density. Then I guess we're also asked about the whether the Z transform of the ACF exists. But then remember, what is the ACF? So the ACF has just this tiny peak at omega equals m, but then other than that, it has this constant term. So actually this constant term, p squared, is quite dominant in the autocorrelation function. But then when you have a constant, just imagine this first part doesn't make a difference. If I give you a function that's constant, and if I ask you to find the Z transform, just like we saw a moment ago, you won't be able to find a common region of convergence for the positive m terms and the negative m terms. If one converges for some z, the other one will diverge and vice versa. So the region of convergence will be empty, or in other words, we just concluded that periodic functions don't have z transforms. The constant function also is a kind of periodic function, so it doesn't have a z transform. So we conclude that x of z does not exist. Does not exist because Rx of m contains a constant term. Okay, now going on with the rest of the question. So in the part C, what we do is we take this original random process. We saw that x of n was Weissen's stationary, it was ergodic, so it has all the nice properties. Now we generate here a new random process, which is very, very tightly related to x of n. Actually, they are very, very tightly coupled. Y of n is just obtained from x of n with a linear transformation. Multiply by 2 and subtract the constant. Now we will first find the mean value and the autocorrelation function of the new random process. Then we are asked whether it's ergodic or not. Now you might actually already ask yourself about your intuition. Whether y is ergodic or not. X is ergodic, y resembles x very much. Would you expect it to be ergodic or not? You might maybe guess that it's ergodic from this kind of intuitive reasoning, but we will also rigorously show that it is ergodic. So now let's first solve this part B. So let's find the mean function of y and the autocorrelation function of y. So eta y is the expected value of y of n. Well, this part, there's nothing deep, it's just simple. We will do simple arithmetics in here. So let's copy the expression for our random process. Expectation is linear, 2 will go outside, then you're left with expectation of x of n. But we know that x is White-Sand stationary, so it will come out as eta x, and then the constant term will go out as itself. So eta y is constant, so we see that y is stationary in the mean already. And similarly, if you look at the autocorrelation function of y, so let's just write down the expression for that. So actually x is real, Bernoulli process 0 or 1, so you could get rid of the complex conjugates. So let's simplify our expressions. So this first y of n plus m term would be 2x of n plus m minus 1, just replaced with the expression. And the second term y of n would be 2x of n minus 1, and closing the expectation. Now what we will do next is very basic arithmetics. We will just, you have two terms in here, you'll multiply them. So the first term, 2x of n plus m times 2x of n. 2 makes already 4, goes out of the expectation. Then you're left with the expectation of this term times this term. But what is it? This is the autocorrelation function of x, right? So for our x of m. And the next term, 2x of n plus m times minus 1. So you have a minus 2 factor times the expectation of this, right? Expectation of n plus m. But since x has a constant mean, this is also equal to eta x. Now similarly here, minus 1 times 2x of n. So you have a minus 2 factor going out of the expectation. So expectation of x of n again makes eta x, and minus 1 plus 1 goes out of the expectation as it's a constant term, so that you get the ACF of y as 4rx of m minus 4 eta x, but eta x was equal to p, so 4p plus 1. This is the expression for the autocorrelation function of y. Now, in the next part, we are asked whether this is ergodic or not. So let's show that it is ergodic as we guessed. So we don't have to go through the same lengthy derivations. The good news is that you could just use some nice properties of the time averaging and then conclude that y is ergodic because x is ergodic. So this part is going to be easier. So let's do it part by part. So in the first part, let's see the time average estimate for the mean of y. So y of n. So this is 2x of, sorry. (2x of n minus 1). Now, the thing here is, well, these brackets, remember that the brackets just denote nothing but a sum, a summation, so infinite summation with some normalization. But whatever properties a sum has, like linearity, constants can go outside, and so on, this we could apply them immediately in here. So, so this constant 2 factor can immediately go outside, because it's actually going out of a summation expression, just we don't write for sake of brevity. So then 2 goes outside, so you have the time average of x of n. Similarly, due to the linearity of the sum, you could separate this term and the second term. You can separate out additive terms. So 2 times the time average of x, and then the time average of a constant is itself. And so since we know now that x of n is ergodic, the time average of x of n is equal to the expected value. So this is equal to 2 eta x minus 1. And here we use the property that x of n is mean ergodic. So 2 eta x minus 1, so this is the time average of the mean of y. But if you just compare it to the true value of the mean function of y, it's also the same, 2 eta x minus 1, 2 eta x minus 1 here. So these two are equal. So, sorry, y, eta y. So since the equality holds, we conclude that y of n is also mean ergodic, just like x. So this is very simply followed from the linearity properties of sums and from the fact that x is mean ergodic itself. So if you do the same thing for the autocorrelation function, or y of m, so the time average estimate of this, so this is y of n plus m, y of m. So these are real, so let's just ignore the complex conjugate sign. So I'll just write down the expressions: 2x of n plus m minus 1. First term, y of n plus m. And then the second term, 2x of n minus 1. So we'll still do maths in here. Again, constants go outside. You can separate out additive terms because these brackets mean nothing but a summation. So 2 times 2, you have 4 times the time average of x of n plus m, x of n. And then the second cross product, so 2x of n plus m times minus 1, so it makes minus 2 times the time average of this term. And similarly, you have here minus 2 time average of x of n. And then minus 1 makes plus 1, so you have this. Now, again, we don't have to calculate anything, we just have to use to observe that x of n is ergodic. So it's mean ergodic and it's ACF ergodic. So since x has this property, what is this time average? Because of the ergodicity, it's equal to the ACF. So our x of m. And what about this term, 2 times the time average? You're just averaging the samples here, just like in here, but you just have a time delay, but it doesn't matter because it's an infinite sum. If you shift by m or not, doesn't change anything. So this is going to be 2 times the mean value of x, because x is ergodic, it's mean ergodic. Similarly, you have here another minus 2 eta x term, plus 1. So what we have here is 4rx of m minus 4 eta x plus 1. Just compare it to the autocorrelation function of y we computed earlier, just comparing to this expression. They are the same thing. So we have the equality. This is equal to our y of m. Time average estimate of the ACF is equal to the true ACF. Just concluding from here that yn is ACF ergodic. So yn is ACF ergodic. It's also mean ergodic. The conclusion is that yn is an ergodic random process. Okay, this last part is very, very easy. It just asks you to plug in some certain value for p is equal to 1 over 2. So just find out the autocorrelation function of y under p equals 1 over 2, and then take its Fourier transform and the z transform, and then find the average power. So it's very simple. I just leave it to you as an exercise. So I'll just give you the answer. So after some manipulations, just start with this. Well, take this expression for the ACF. You know what this is given in the question. Write down a function. You'll have a function of m. Actually, it's gathering the terms together. It's easy to show that our y of m, after arranging the terms together, these terms will simplify. We will cancel each other. So this is going to be equal to the impulse. A single impulse at m equals 0. And then then you can take the Fourier transform of the impulse, the Z transform. So any impulse only at m equals 0 will have a constant dTFT equal to 1. Similarly, very similarly, if you look at the Z transform of this Sy of Z, you will also get 1. And the region of convergence here, I'll let you work on this, but then you can show that the region of convergence is the whole complex plane. No part of the complex plane is excluded. And also, if you look at the average power, very simply, you should look at the autocorrelation of y at m equals 0, but then simply going to be equal to 1. So this concludes the questions about the sorry. So this is the part of the exercise session about the topic of the PSD. Okay, so in the last chapter, in the next chapter, we're going to start a new chapter. In the last lecture, we're starting a new chapter. It's going to be about the LTI stable filtering of random process. We'll simply have filters, and then random processes will enter, and we'll observe random process at the output. It's a very fundamental topic in signal processing. So if you wish, we can go like this, 2 videos for each chapter. The first one on the theoretical part, second one on exercise, so that you have the liberty to look into the exercise as you wish. So, okay, I hope you're all still doing very well, and then see you in the next lecture.